How's everyone doing? Is doing good? Woo! Yeah. My name is Nick Steele. I'm a physical science technician here at Grand Canyon. I've been here for about 4 years now. And today I want to talk to you guys about the springs and aquifers of Grand Canyon. The whys, the whats, and the hows. I'm on a little clicker. And before I get too far into springs and aquifers, I do want to let you guys know that physical sciences, besides springs and aquifers, we also do maintain our air resources. So we maintain 2 air pollutant monitoring stations on the South Rim that measure stuff like ozone, dry deposition, particulate matter. We are also in charge of managing the park's caves, along with the paleontology resources. Okay, so let's dive into hydrology. So first off, we need to discuss why do we care? What's so important? And this is pretty easy to understand. So, if you just go on Google Earth, you look at satellite imagery, you look at the Grand Canyon and you'll just notice a whole lot of brown, a whole sea of brown. And, like my wife is from Costa Rica, and when I first brought her here, she just, she couldn't get over, Arizona, it's brown, it's really dry. But every once in a while you look at this imagery and you see these dark green patches down in the canyon. These green patches, these are our springs. And you hike down to them, you see these rich riparian, forests essentially. And these are springs. My point with this is that the life cycle and the water cycle are one. Species diversity around our springs is 250 times greater than anywhere on the surrounding desert. Additionally, oh, there we go. Wait for it. I think I broke it. Additionally, Grand Canyon's entire ability to operate on the South Rim for the 6.5 million visitors that come here, along with all the residents who live here, is completely tied to the water resources of Grand Canyon. I don't know if you guys know this, but there's a pipeline that goes from here all the way down the South Rim and goes 3/4 of the way up to a spring called Roaring Springs, which is what this is right here. And we literally pump that water all the way over here. So our ability to operate and live here also depends on the water. And yeah, if I didn't drive this point home yet, there's also significant cultural value to our springs. And they're just simply, wait for it. Is it the trigger button? Oh, there we go. And yeah, they're just simply some of the most. Forwards, backwards, laser. Oh, gotcha. Okay. Yeah, they're just simply some of the most beautiful places in the canyon. And currently, right now, Grand Canyon. We're facing greater threats to our water resources than we ever have in this park's history. We have increased visitation, which has put an increased demand on our water resources. We have climate change, which is reducing the snowpack on the North Rim and is creating a more erratic recharge, which is ultimately decreasing the supply of our water resources. And we have contamination issues. We have bison on the North Rim, trampling springs, trampling sinkholes, and we have uranium mining, which, there's a lot of unknowns associated with that. Okay, so apparently I'm going to click through this every time. But so what it comes down to is that we need to better understand our vulnerabilities to these different threats. We need to understand our flow paths. Where is the water coming from? How long does it take to get to our different springs? And then what is our water budget at Grand Canyon aquifers? How much water and resiliency do we have to these threats? So everything we do in physical sciences is pretty much trying to understand this one graphic. We try to understand how does water enter, how does it flow through, and how does it emerge out of this big, thick pile of rock. So we have our sea aquifer we're trying to understand, which is kind of this hydrostratigraphic unit at the top. That's the Coconino Sandstone, Toroweep, and Kaibab. And then we also have the Redwall aquifer, which is the Redwall and Muab limestone. And then we want to try to understand how are these two water bodies connected and how they're communicating. And our primary means to studying our aquifers is springs. Springs are our windows into our aquifers. This is how we collect data on our aquifers. Additionally, when we talk about Grand Canyon hydrology, we have to talk about karst, because karst adds significant complexity to our groundwater system. That's because how water moves through karst is much different than other types of rock. Karst is essentially what limestone will form when water moves through it. Limestone doesn't have a lot of porosity. It is a soluble rock, so water will move through preferential weaknesses, through faults, fractures, and form these large conduit systems. Like, do you guys remember the Windows 95 screensaver, 5 screensaver? So this is essentially what we're trying to understand right here. So really complex. It's a piped network. And so what's the implications of karst? So this plot right here says it all. So these top two is at Roaring Springs. This is discharged water coming out of the spring, and then this is water temperature. And then this plot here, this is precipitation on the North Rim. And what we see is that there was this monsoon event, June 10th, 2015 apparently, 2015, and within 2 to 3 days, we see a response in Roaring Springs. So within 2 to 3 days, water from the top of the Kaibab Plateau goes through about 3,500 feet of rock and comes out at the spring. So this has serious implications when we talk about recharge and we talk about storage of these aquifers. So kind of talk more about the hows now, how we're trying to understand our system. So a tool we use to try to break down this problem is we try to delineate ground basins and determine catchment areas. And what this essentially means is we're trying to map that Windows 95 pipes screensaver. So we're trying to figure out flow paths and travel times. The first attempt was in the 1970s by a hydrologist named Peter Huntoon. And based off structural controls and stratigraphic controls, this is the map that he created, kind of dividing these different basins for each spring. So in 2015, 16, 17, we wanted to test Peter Huntoon's model. So we did a series of dye traces, and dye traces, what it essentially is we have these fluorescent dyes. We did 5 of them over the 3 years, and we'll pour them into sinkholes, and then we'll bug our springs, and we'll see where does that dye come out. And what the take-home message of all this dye tracing is we realize that our system is much more complicated than what Peter Huntoon originally envisioned. That's because all these dyes that we put in the Bright Angel basin that he marked, they didn't quite go to Roaring Springs like we hoped. Pretty much we learned everything goes to Vasey Paradise. Doesn't matter what, they'll all go there. But we put these dyes in this basin, and a lot of them ended up going north along these big faults, and then coming down into Peats and also down in Shinemu. And then we also had this one dye that came down and hit all the north side of the Bright Angel Creek, but nothing in Roaring. And then we finally got a hit in Roaring Springs in 2017 with this dye right here. So yeah, our system is much more complex than we were thinking. So to talk about a little bit more recent studies, we had a grad student at NAU who past few years has been working to just kind of understand the sea aquifer a little bit better. So in the study, he went on the North Rim and essentially took monthly samples or bi-monthly samples of ions and isotopes from 22 different springs. And the whole purpose of this is kind of the idea is if we can understand our C aquifer, we can understand our R aquifer, then we can kind of start understanding the connectivity between both of them. And so with this, he kind of just discovered a couple different things. So he was able to break this down into really 3 distinct water bodies or distinct regions of the Coconino Aquifer. So in the north, we kind of have this system that seems to have a little more resonance time. Coconino sandstone actually tends to thinnen the more north you go. So these springs tended to have more chloride and sulfate from the toroidal formation, and they also didn't respond to precipitation, not super rapidly. Then kind of in the intermediate, we had this section where they had higher calcium carbonate water, and then it did respond a little bit more to precipitation. And then this stuff was just really quick right through the system, didn't pick up any ions. So pretty interesting. And then also we did stable isotope analysis with this, along with our aquifer springs, Redwall aquifer springs down in the canyon. And through this analysis, we found that recharge is really heavily biased towards snowmelt, the snowpack, to winter precipitation. Another study we're doing is Natalie Jones. She's been a technician working with us, and she has published a paper on trying to just model the contamination vulnerability of the aquifers. So she essentially took a sinkhole density map, combined it with a bunch of stratigraphic information, precipitation information, put together a model, and came up with these models. And the take home of this is that high sinkhole density is located near locations of greatest infiltration, so near major faults and fractures. And then there's large swaths of the plateau, because it's karst, dealing with quick responses. Both of our aquifers have pretty high vulnerability. Another cool study that we're doing, this is a little bit exploratory. We sampled over 100 unique spring sources and creeks in the canyon for environmental DNA. So this is literally take a water sample and you can see what DNA is in there, what species. And this is a little exploratory, but we kind of want to try to define water basins with this. And kind of a more direct, less abstract way to think of this is up in North Canyon Wash, there's a creek up here, and it has a lot of water, but once it hits the Coconino, it just sinks, just completely disappears. It's really neat. But in that creek, we have Apache trout. And we're pretty sure this creek is connected with Vasey's Paradise over here. So the idea is if we sample Vasey's Paradise, we pick up Apache trout, guess what? We have this connection between North Canyon Wash and Vasey's. So it's kind of a unique, different way, different approach at trying to solve this stuff. And then, yeah, some other hydrology projects. We're doing some precipitation response analysis. We're exploring the connectivity between monsoon precipitation and springs. And then, because we have these really quick responses, we're potentially trying to use this actually as a tracer, which is kind of interesting. Also, in spring and fall of 2019, we went to the Shivitz Plateau, which is on the north side, western Grand Canyon, and we did the first ever robust spring sampling out there, hit a bunch of springs and collect a bunch of data. So yeah, and just want to let you guys know, all our work, we don't like to keep it in a black, dark box. Everything we do, we try to publish, get it out, peer reviewed. So everything we do is available, and I'll provide some of the stuff, and you guys email me. I can provide whatever publications you guys want. So yeah, to summarize, what do? We're trying to understand this strat column and how water flows through it. Why are we doing it? Because all life depends on it. And how are we doing it? Science. Yeah.